by Marco Fenucci from University of Belgrade, who is going to speak about the distribution of small near-Earth objects and the role of the Yarkovsky effect.
Okay,
so,
thank you, Boyan.
Marco, please, stage is yours.
Okay, thank you. Thank you, Boyan. So, as I said, I'm going to talk about the distribution of small near-Earth objects and the role of the Yarkovsky effect. So I'll go through a brief introduction, then I will speak about the transport mechanism of objects from the main belt to the near-Earth region. Then I will talk about the modeling of the population of small NEOs, and I will finally talk about the magnitude of the Yarkovsky drift. So, as today we discovered more than 20,000 NEOs, and here in this picture we can see the size frequency distribution of the discovered objects in blue. And we can also see the comparison of the models of some recent models of populations of NEOs. And these models agree that the catalog is full for absolute magnitude less than 17.5 magnitudes, and the catalog is at about 94% for objects larger than 1 kilometer in diameter. On the other hand, models predict about 50,000 objects with diameter larger than 100 meters that still pose a threat to activities on Earth. And they also predict about 100 million objects with diameter larger than 10 meters. And here from the picture, we can appreciate the fact that at 100 meters, the catalog is far from being complete, and at 10 meters, it's really far from being complete. So to discover these small guys between 10 meters and 100 meters, we have to rely on some models that tell us where we can find them in the space. So to this purpose, we take the last model, which is the model by Granvik, and we see how it is constructed and how it could be extended to smaller sizes. So the model by Granvik provides a 4-dimensional orbital distribution of NEOs in semi-major axis eccentricity, inclination, and absolute magnitude, and it is valid for magnitudes in between 17 and 25. So it doesn't go to very small sizes. And moreover, it is based on the transport mechanism of objects from the main belt to the near-Earth region, which I'm going to introduce next. And the basic modeling equation of this Granvik model is the following one. So on the left-hand side, we have an observed population by some survey. And on the right-hand side, okay, we have a bias given, which is associated to the survey. And then we have the true population, which is composed by the contribution of each source region. The true population of each source region depends on the absolute magnitude and on some fit parameters, which are computed trying to matching the observed population and the model. And then we have the orbital distributions. And these orbital distributions basically are describe where objects coming from a specific route are more likely to be present in the space of semi-major axis eccentricity and inclination. And they are basically computed integrating a lot of test particles. So these are a fundamental piece of the model, and for this reason I want to talk briefly about this transport mechanism. So we know that in the main belt region, the main belt region is filled by a lot of mean motion resonances with Jupiter, which mainly cause changes in eccentricity and inclination. So if an object is trapped in a mean motion resonance with Jupiter, the eccentricity can be pumped up, and eventually this object arrives to the near Earth region. Besides mean motion resonances, we have also secular resonances, which are, for instance, the Nu-6 secular resonance with the node of Saturn. Besides these gravitational effects, we have also non-gravitational effects, such as the Yarkovsky effect. And the Yarkovsky effect is a recoil force due to sunlight. Indeed, these objects are heated up in the sun, and they radiate energy in the thermal wave band, and this causes a small and continuous thrust. And basically, the main effect of the Yarkovsky effect is a change in semi-major axis, and this change is positive if the rotation is prograde, and it is negative if the rotation is retrograde. And more importantly, the drift is size dependent, and it scales as 1/d. So this means that for small guys, the size could be much faster than for larger objects. And beside this size dependency, the total drift depends also on physical and thermal characteristics of the asteroids, such as the density, the surface composition, and thermal properties too. So here we can see a final example of transportation. So let's suppose to take an asteroid on the left-hand side of the 3-to-1 Jupiter mean motion resonance. And let's suppose that the rotation is prograde. So this object suffers the Yarkovsky drift, and the drift is positive, so this object is moving to the right in this plot, and eventually it arrives to the 3-to-1 Jupiter mean motion resonance at 2.5 astronomical units. Then, by effect of the resonance, the eccentricity is pumped up until the asteroid reaches the near-Earth region. And in the near-Earth region, this asteroid can undergo some close encounters with planets which change all the orbital elements. So what we want to do is to, as I said before, take the Granvik model and try to extend it to small guys. And the main motivation is that in the Granvik model, the Yarkovsky effect is not included in the dynamics of the NEO region. But however, this was fair for their model because for the size range that they take into account, the Yarkovsky effect is not very relevant in the final outcome. And also the Yarkovsky effect could be large for very small asteroids, so we want to test this. And so our aims here are to understand how the basic components of the migration model are affected when we introduce the Yarkovsky effect. And we want to understand how fast should be the drift to see some results, some different results in the main components of the model. And finally, we want to understand if the typical drifts of these small objects from 1 meter to 100 meters in diameter match with the Yarkovsky drift, for which we see some differences in the outcome. So to test this, we perform some numerical simulations, and in particular, we want to test two transport routes that are included in the Granvik model. So to perform these numerical simulations, we take initial conditions from the Granvik model, and we select two routes. The first one is the 3-to-1 Jupiter mean motion resonance, and we take 1,000 objects, 500 on the left-hand side of the resonance and 500 on the right-hand side. And here in the central panel, the red dots corresponds to our choices of initial conditions. The second route that we take into account is the Nu-6 secular resonance, which is very important because it's the one that produces more Earth impactors. And also here we take into account 1,000 objects. Then, given the initial conditions, we perform these numerical simulations in a dynamical model, which includes the attraction of the Sun and the 8 planets from Mercury to Neptune. And we add a constant Yarkovsky drift in the near Earth region, which is implemented as an acceleration along the velocity. For the numerical integration, we use the Mercury integrator, which uses an hybrid scheme which alternates a symplectic scheme to a Burlish-Stowe algorithm to treat the close encounters with planets. And also this algorithm uses a variable time step, and we set the maximum time step to 12 hours. And we propagate forward the dynamics for 10 million years. So what we want to do is to take the previous initial conditions, give some magnitude for the Yarkovsky drift, and see how the results changes. And in output, indeed, we record the oscillating elements every 250 years, and then we compute the average time spent in the new region and the orbital distributions associated to these two routes, which are the 3-to-1 and the secular Nu-6 resonance. Here we can see some results for the lifetimes of objects entering through the 3-to-1 Jupiter mid-motion resonances. So on the left-hand side, we can see the results for the inner part of the resonance, and on the right-hand side for the outer part. So for the inner part, we can see, okay, the blue circles correspond to our simulations. And we can see that as the magnitude of the drift increases, the lifetime is decreasing. And on the other hand, for the outer part, the drift is negative because objects have to come close to the 3-to-1, so the drift should be negative. And here we can see that as the magnitude of the Yarkovsky drift increases, so we have to read this plot from the right to the left, also the lifetime increases. And we can also appreciate the fact that these changes are fitted very well linearly with the magnitude of the Yarkovsky drift. So further, we can see also the orbital distributions. And in the first row, I'm showing the results obtained in a purely gravitational model. And in the second row, it's the same distribution, but obtained using Yarkovsky drift of 0.1 astronomical units per million year. And we can appreciate the fact, for instance, that in the plot in semi-major axis and eccentricity, the distribution of these objects is more spread along the resonance line here, rather than in a purely gravitational model. And for the distribution in semi-major axis and eccentricity, it is a bit wider at small inclinations. For the Nu-6 secular resonance, the trend of the lifetime is similar to the outer part of the 3-to-1 mid-motion resonance with Jupiter. And indeed, also here, objects coming from this route have a negative drift, and the lifetime is increasing for increasing magnitude of Yarkovsky drift. And another interesting fact regards the collisions with the inner planets. And as I said before, the Nu-6 resonance is the one that produces more impacts with Earth. So in these simulations, we took into account also the collisions with the inner planets. And we can see that also here, as the magnitude of the Yarkovsky drift increases, the number of collisions with inner planets increases too. And the trend is also linear. And for instance, when the drift is 0.1 astronomical units per million year, the number of collisions is almost double. So the Yarkovsky drift could also produce more impactors with the inner planets. Here I'm showing similar results to the previous one. So I'm showing here the orbital distributions. And also here we can appreciate the fact that when we introduce the Yarkovsky effect, so when looking at the second row, we can see that the distribution is more spread inside the NEO region, and this is seen much better in the semi-major axis inclination distribution. So at this point, from these experiments, we can conclude that if the Yarkovsky drift is fast enough, of the order of 0.05, 0.08, 0.1 astronomical units per million year, the basic components of the migration model are affected. So now the true question is if actually these small guys can reach this fast Yarkovsky drift. And as I said before, the magnitude of the drift is proportional to the size of the asteroid, and it scales as 1/d. And here, from the measurements performed by Granvik et al. In this paper in 2020, where they measured the Yarkovsky drift for 250 objects, more or less. They fitted their measurements with 1/d, and they confirmed this trend for the magnitude of the drift. And here we can see, for instance, that for objects of about 50 meters in diameter, the drift is about 10 to the minus 2 astronomical units per million years. So we are coming closer to our to the magnitudes that we need to find some differences in the outputs. And also looking at the databases of measurements of the Yarkovsky drift, we can find actually some objects with a fast Yarkovsky drift of the order of 0.04, 0.05, 0.01, and there's also a very small objects for which the magnitude is almost 0.02 astronomical units per million year. So these measurements already provide some clues that small guys can actually reach the level of drift that we need to see some changes in the orbital distributions and in the lifetimes. And to understand better which are the characteristics that an asteroid should have to reach these fast drifts, we constructed a model, and which is based on a mathematical modeling of the Yarkovsky effect. So this model takes in input a near-Earth object with a measured Yarkovsky drift and a measured rotation period. Then, using a mathematical modeling of the Yarkovsky effect, which depends on the semi-major axis, from the density, from the surface properties of the asteroids, and from the inclination, we modeled some distributions of these parameters, and we try to extrapolate informations about the surface properties of the asteroid, inverting the equations of the modeling of the Yarkovsky effect. So comparing the model to the measurement, we can find some clues about the surface properties of the asteroid. And then performing a Monte Carlo simulation, we can produce in output a density function for these thermal properties, which is the conductivity of the asteroid. And we are particularly interested in this conductivity of the surface because it the drift. Yeah.
About 5 minutes left.
Okay, thank you. Because the thermal conductivity affects the drift, and it can change the magnitude of the drift of some order. So here, for instance, I'm showing the magnitude of the Yarkovsky drift as a function of the density of the asteroid and the thermal conductivity of the surface. And here on the left, the size of the object is 10 meters, and here on the right, the size is 5 meters. So from this plot, we can conclude that, and here I'm showing some level curves of the Yarkovsky drift. So from these plots, we can conclude that when the thermal conductivity is low, the Yarkovsky drift is larger, and it has to be low in between, let's say, 1 and 10 to the minus 4 to see some significant change in the Yarkovsky drift. And from these plots, we can see that in some cases we actually reach the drifts that we need to see some differences in the orbital distributions and on the lifetimes. So further, to understand if small asteroids can actually reach these small conductivities, we applied our model to two small asteroids, which are 2011 PT and 2012 TC4, which are two small and fast rotators because they are, okay, one is about 45 meters in diameter and the other one is 10 meters in diameter. And they rotate with 11 minutes period. And here I'm showing the density function of the thermal conductivity. And we can appreciate the fact that the most likely values of this parameter are very low because they are around 10 to the minus 4 and 10 to the minus 2 for 2011 PT, and 10 to the minus 5 and 10 to the minus 1.5 for 2012 TC4. So this shows that actually also small guys and also fast rotating asteroids can have this small thermal conductivity of the surface, which was kind of unexpected because these small values of conductivities are mostly associated with the presence of regolith or dust, or in general a thermal insulating layer on the surface, which is questionable if a small fast rotator can retain it. But from these results, it seems that it is possible, and it is not clear how it can be achieved, however. So in conclusions from these considerations and from these simulations, we can conclude that the Yarkovsky effect causes significant statistical changes in the lifetimes and in the orbital distributions, and that and they need a fast drift to see these changes, and these fast drifts can be actually reached by small asteroids. And of course, there's still a lot of work to do, and we want to introduce a variable Yarkovsky effect in the NEO region in the next. And of course, we want to understand better which are the typical drifts for different sizes and for different asteroid compositions for different source region. We want also to simulate the migration of small asteroids from the main belt to the NEO region. So that's it, and thank you for your attention.